So in the same vein, we have to prove that root 3 is irrational, right? We go through the same routine. If we don't get a completely reducible form, then we realize that what it's wrong. So the same procedure, we assume it's rational. So we express it as what A over B. Then we square both sides and we simplify. So when you square both sides, this what 3 is equal to A squared by B squared. And when you simplify, you get this expression. Um, that's for the basic step, right? Now, what you can infer from here is that what A is a multiple of 3. So A is a multiple of 3 of 3. Therefore, what we can do is that we can say that let A be equal to some constant C times 3, right? We are multiplying by 3 to ensure that what A is always a multiple of 3, right? Realize that when multiplying a constant by 3, you get a multiple of 3. Now, we can put A back into this equation. And that gives us 3B squared equals 9C squared. Now, when you divide both sides by 3, realize that I get B squared is equal to 3C squared. So C is also a multiple of 3, right? Which goes to contradict this fact that these are in the reduced final form, right? Because they cannot be both in a multiple of 3 and A and B be not be in their simplest form, right? So that's what the rationality means. So we can go ahead and they said every rational number may be expressed as a terminating decimal or recurring decimal. So terminating means that it ends in decimal places. Recurring means that decimal places terminate continuous, right? Every irrational number can only be expressed as a non-terminating decimal. But these things are actually useful for your section A's, right? So that when they make a statement, it just sounds right, right? You just know what it means, right? You can't express an irrational number in the form of A over B. So the only way is that you can continue to write the terminating portions. It's the same thing for pi, right? Pi is irrational. Now, we are about to do the set of real numbers proper. Now, when you combine the set of real numbers with the set of rational numbers with the set of irrational numbers, you get real numbers. And relax, in a minute, you know why they are called real numbers, right? So the every real number corresponds to exactly 1 point on the line, right? And every point on the line corresponds to a real number, right? Now, this is called the real number system, and you will know later. So the operations with real numbers, which you can verify, the closure law. When you pick any two real numbers, provided that you are not dividing by 0, right? There is closure, right? Any of the 4 binary operations, addition, subtraction, multiplication, division. Once you do it, you get an element still in the set of real numbers. There's the commutative law. It means that it doesn't matter the order of operation, right? In addition, and also for multiplication too, right? So 2 times 3 is the same as 3 times 2. A plus B is the same as B plus A. Think these ones, distributive law, I think multiplication is distributive over addition, right? So it means that when you have A multiplying the expression bracket B plus, you can represent it as AB plus AC, right? And there's existence of identity under addition, existence of identity under multiplication. I hope you remember your identity element from binary operations, right? So identity element is an element such that after the operation is done, it remains invariant, or the operand remains invariant. So, for example, in addition, the identity element is 0. So when you do A plus 0, right, the operand A changes, it still goes through. In multiplication, it is 1. So when you do A times 1, you realize that the operand A doesn't change, right? That's what it's saying. Then there's existence of inverse, right? And addition, the same thing for multiplication, right? So the inverse is anytime you operate it on that, you get the identity element. This is what I'm trying to say. The operation here is addition, right? So when you take A, you operate it on the element X, right? Now, if x is the inverse of a, you get the identity, and identity and addition is 0. It's the same thing you can say for multiplication. Now, any set which satisfy all the above rule is called a field, right? Now, that's a special name for a set which can satisfy all of these above rules. So, you say the set of raw numbers from a field. It's more of abstract mathematics, but we'll get into that. And the there are other concepts, right? And usually this comes in when you are doing more of logical maths or application of logic, right? So it may sound a bit abstract now because you are studying it in separation. But here's all what it says. It says if you have A, B, and C, right, which are members of the set R, right, then it is either A is greater than B, or A is equal to B, or A is less than B. What it's saying that is that in the set of raw numbers, right, or all the numbers we can use in this world, when you pick any two of them, right, they will either satisfy one of these. Either one will be greater than the other, or less than the other, or they'll be equal to each other, right? Now this law is called the law of trichotomy, and you'll see such later. Now there's also another law, right, and this is kind of fun. So it says if you have A which is greater than B, and B is greater than C, then automatically A is greater than C, right? It's called transitivity, right? It means what it actually shows you is that there is a natural ordering among the set of real numbers, right? Now, when you go to complex numbers, you may see something different, but here's what it says. It means that when we pick any three real numbers, so let me take 2, 5, and 7, right? Now, if I know that 2 is less than 5, right? And I also know that 5 is less than 7, right? Then because of these two conditions, I can infer that 2 is what? Less than 7, right? Yes, it sounds very simple. That's what should happen here. But in actuality, you realize that you'll be using it without knowing. So take note of it. It's called transitivity. Now, you realize that if A is greater than B, then A plus C is greater than B plus C. This one is also simple. When we pick any three numbers, say 2, 5, and 7, like what we did previously. Now, let's say we already know that 5 is greater than 2, right? Now, if I add 7 to both sides, right, once the number I've added here is the same for both sides, then this operand greater than still holds, right? This is also very simple and logical. You can know. Then we can go on to the next part, which talks about if A is greater than B and C is greater than 0, then AC is greater than BC. You know, these laws, you can just pick any two numbers and try it on them, right? So the same 2, 5, 7 we used, right? Now, if A is greater than C and if A is greater than B and C is greater than 0, so this is our C. Now let's assume this is our A. So 5 is greater than 2, right? Now also, if we multiply through by 7, so 7 here, 7 here, because 7 is greater than 0. If you multiply through by 7, you get 35. It will be greater than what? 14, right? And this will hold once you are doing it rightly, right? Now, when you consider the reverse where A is greater than B, but C is less than 0, then realize that you switch signs, right? So instead of 7, maybe if I had negative 7, you realize that here becomes minus 35, here becomes minus 14. Right, let me write it for. Instead of 7, if I had minus 7, realize that here becomes minus 35, and here becomes minus 14. Right, when I do 2 is times minus 7. I realize that minus 35 is less than minus 14. Right, so that's what that rule says. And it sounds very basic as a law. You've probably used it so many times, but you get more hold of it now. Now, we try to identify an operation called the absolute, right? Now, the absolute operation says that if I give you an absolute of x, right, then the value is x for x greater than or equal to 0, or the value is what? Minus x for x is less than or equal to 0. So this is what it means. When you have any number and you put it in the absolute sign, right, you get a positive form of the number, right? Now, I know you are probably wondering, they said minus x here, so why do we always get a positive answer? Well, if x is less than 0, then it means x is negative. So negative times negative will give us positive, and that's an example you see here, right? But you can just keep it in your head. Anytime you take the magnitude of any number, no matter what is inside, you get a positive version, right? So that's what you see. And there is also a theorem which holds for inequalities. An example is that when you take the magnitude of the product of two numbers, right, it's equivalent to taking the magnitude individually and multiplying them, right? So when I have minus 3 times 2, it's the same as me doing minus 3 times minus 2, times positive 2, sorry, right? That's what that means. Now, there's also another triangle law of inequality, and usually it gets hard for people to behold, so take note. It says that if I add any two numbers, right, and find their absolute, the absolute will always be less than finding the individual sum in absolute, right? If you find it difficult to wrap your head around, see something like this. If I do minus 3 plus 2, what do I get? I get absolute of minus 1, because minus 3 plus 2 is what? Minus 1. And this gives me positive 1. Now, if I do minus 3 plus 2, I have to evaluate what is in the absolute first. So I'll get 3 plus 2, right? And this will give me what? 5, right? So realize that 5 is greater than 1. And that's what they are trying to show here, right? It is called the triangle law of inequality. Then the reverse actually holds for subtraction. If I subtract any two numbers and find their magnitude, it is always greater than me finding the magnitude of the difference of the individual numbers. And you can try that yourself. Now, if I find the magnitude of a number and I get 0, then it implies that the number is 0. And yes, that's also reasonable to understand. Although all these laws have been stated so simple, so not unique to appreciate, they are actually the foundation of many proofs you'll be going through now. So take note of them. Yes, and you can also extend this property. So when you have a long multiplication of real numbers, you can take their individual magnitude and multiply them. It can also be applied on the addition side all the time. Now, these things, you usually use them when you are doing an addition of a lot of numbers, but you're trying to approximate it, right? Yes, it's used in advanced analysis, and we'll see an example of that. So they try to make you solve an example. So let's quickly go through that. It says, prove that the magnitude of xy is equal to the magnitude of x multiplying the magnitude of y. Right now, you see, once you are asked to prove, if you try to go the normal route, then you have to try every possible way. So you realize that here they are trying every possible way, right? So they tried the first way. Let's assume x is equal to 0, y is equal to 0. That's one case. Now, when they are both greater than 0, that's another case. Now, when x is less than 0 and y is greater than 0, that's also another case. And when they are both less than 0, that's another case. Why? Because they are trying to go through the direct route of proof, right? So they tried the first one, and yes, magnitude of 0 times magnitude of 0 is what? It's still 0, so it satisfies x and y. But that was not enough. They had to do for the next one. If x is greater than 0 and y is what? Greater than 0, then you realize that when you find the xy, it will be greater than 0, right? Which means that it will be equivalent to what? The magnitude multiplied. Now, when you try for the negative side, you realize that the magnitude will take care of the negative, right? So at the end of the day, you come and get the same results. And yeah, when you do for the reverse too, you also get and the same results. Now, Because all of these four worked, right, the proof is correct. That's why I said you have to show for all instances that the proof is correct before you can confidently say that the statement was true, right? And that's what we use in mathematics.